In this presentation, we're talking about the use of absolute value functions and their transformations. That's the entire section. This is going to be a two-part video. And so the first part we're going to focus solely on is just the absolute value portion of the section. Our objective in this presentation is to get an understanding of how to graph an equation that is written in the form y equals some constant times the absolute value of x minus the constant plus another constant outside. So what we're going to try to do is determine what does a, h, and k do to our actual absolute value graph. So before we begin, we're going to go ahead and take a step back and revisit what it means to actually be absolute value. The definition of absolute value tells us that the absolute value of x is the distance that that value is from 0. The key part here is that absolute value is representing a distance. Why is that key? Because a distance can never be negative. All right? Distance is always going to be positive. You're going to see that in our graphs as we continue. So, if I were to graph the absolute value of x, I could begin by setting up a table of values. So, the absolute value of -2 is the distance -2 from 0, which is 2. The absolute value of -1 is 1. Absolute value of 0. Absolute value of 1. Absolute value of 2. So, if you look at the word absolute value, basically what we're observing is just the value of the number, not actually the sign, which is also related to its distance. So now if I take my table of values and actually plot these points, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. I get the following graph, and I apologize, but my handwriting is not the best. And this should look familiar because an absolute value function produces a graph that we call V-shaped graph, right? Where two linear lines that connect at a point that we're going to refer to as the vertex. Now, before we progress any further, one thing I'd like to show you is upon graphing the absolute value of x, you can see that no portion of the graph is down in the negative portion of the y coordinate plane. Again, the reason for this is because we're talking about a distance that a value is from the origin, and that distance is always going to be positive. So, as we progress, we're going to go ahead and now look at what a, h, and k, how does that transform our absolute value function? And to start off, what we're going to do is we're going to look at the constant a. All right. So, what we're going to do is we're simply just going to take a look at a times the absolute value of x. And what I'm going to do is I'm going to use two different values. I'm going to use 2 and I'm going to use 1/2. Now, before I begin, I'd like you to just think for a moment. What do you think is going to happen, if you will, to our original graph if I place a constant 2 in front? If you want to, you can pause the video at this time. Not you. Oh, not you. If you want to, as you're watching this, you can pause the video. But I'm going to go ahead and progress. So, if I graph 2 times the absolute value of x, I'm still going to have the point 0, 0. If I substitute a 1 in for x, that's now going to give me a value of 2. Because the absolute value of 1 is 1 times 2 is 2. If I put 2 into the equation, that's going to give me a value of 4 up here like so. Now, going the opposite direction, if I put -1, well, the absolute value of -1 is still positive 1. So we're still going to end up there. And at -2, we're still going to have a value of 4. So now, you see we still have the same shape, which is always going to be true. We're always going to have a V-shaped graph, but it's going to be slightly different. Now, you might not be able to tell the difference yet, but something should pop out now as I go ahead and show you what happens when we use an a value of 1/2. If I use an a value of 1/2, we still have the origin as a point. But if I substitute the value 1 in for x, the y value is 1/2. And if I put the value 2 in, the y value is 1. And I know it's symmetrical, so I'm just going to go ahead and plot the other side. So now we have our red v and basically our green v from their respective equations. To tie this all together, if I were to replot the original function, y equals the absolute value, we would get our following v like so. This leads us to the following conclusion. A is what we call either a stretch or a shrink. Stretch means that we're actually going to increase more rapidly vertically. That happens when we have an A value such that the absolute value of A is greater than 1. So if our A value is greater than 1, then it's going to increase, or it's going to actually get vertical more quickly. We'll shrink it, or we'll actually flatten it out in this case, if the absolute value of our A value is less than 1. Now, one thing to realize also is we're not going to have an A value equal to 0. If you think about if A were equal to 0, that would just eliminate our absolute value, and therefore we would have a horizontal line at the x-axis. So we're going to look predominantly at A either being greater than 1 or less than 1. You also realize that it's not equal to 1, because again, if A were equal to 1, then it wouldn't have any manipulation to the graph, and we would just be along the black graph as originally stated. So, in conclusion, as far as A goes, A is either going to be a stretch or a shrink. Now, continuing over to the next phase. Now, we're no longer going to have an A value, but we're going to have a value that we're adding outside the absolute value. So, again, while I prepare this, you can think, how do you think adding or subtracting a value outside the absolute value will affect the graph? And as we look at our graphs, you could see that if I substitute 0 in for x, this would be 0 plus 3, which takes me now up to here. If I substitute 1 in, 1 plus 3 would be a 4. And then 2 plus 3 gives us 5. And then, again, if we check the -1 and -2, we get the same thing. And based off your graph paper, your V's will look respectively either skinnier or flatter. As you can see, I have a pretty long x-axis in this case. That's why it looks fairly flat. But the key point to visualize here is the fact that now our vertex is no longer at the origin, but it actually moved up the y-axis. So I think we can rationalize then, if I subtract 3 by putting our values in, 0 would give me -3. If I substitute 1, 1 minus 3 is -2. And 2 would give me -1. And I get the following. We see that we basically get the exact same shape, right? But the only difference is the vertex is located in different positions other than the origin now. That's why we're going to say K represents our vertical shifts. So, our vertical shifts, right, if K is positive, that's going to shift our V upwards. If K is negative, it's going to shift it downwards. So now, one thing to note is we can have an absolute value graph down in the negative portion of our coordinate plane, but that will only occur if we're subtracting a K value outside the absolute value. Then we have one last manipulation, and that's if we're adding or subtracting a value inside our grouping symbols of absolute value. So now, if I look at this graph, if I substitute 0 in for x, 0 minus 2 is negative 2. So the absolute value of negative 2 is 2. So by substituting 0 in for x, I actually get the value of 2. If I substitute the value 1 in for x, 1 minus 2 is negative 1. Absolute value of negative 1 is 1. So by substituting in 1 in for x, I get the value 1. And by putting a 2 in for x, 2 minus 2 is 0. Absolute value is 0. Now, just for sake, I'm going to go ahead and continue down the right side, because if I substitute 3 into this, 3 minus 2 is 1, and the absolute value of 1 is 1. And by substituting 4 into the equation, 4 minus 2 is 2, absolute value is 2 is 2. I should actually do this in green so we get the following. It's going to look a little bit off. I know I didn't pass that point. We're going to actually do this. There we go. So that way it looks like it's symmetrical. So now we are actually adding or subtracting a value inside the grouping symbols. It didn't move it vertically, but you can see it actually shifted our graph to the right. If we look at our other example, if I start off again with substituting 0, 0 substituted in for x gives me 2. Absolute value of 2 is 2. So I'm still going to be passing through this point. But this time I'm going to go to the negative 1. Negative 1 plus 2 is 1. Just going to put it right there. And then negative 2 is going to give me a value of 0. Negative 3 will give me 1. And negative 4 will give me a value of 2. So now you can see by either adding or subtracting a value inside the parentheses, that's actually our horizontal shift. So H represents our horizontal shift. So now where this leads us to is, if we go back to the original, we wanted to be able to graph an absolute value function in this notation. So to wrap everything together, putting all three concepts together, we can now look at the following example. Let's say y equals 2 times the absolute value of x minus, let's say, 3 plus 4. This would be the most extreme scenario for us to actually graph. So what this is going to tell me is my v is going to shift to the right 3 and up 4. Right there is going to be the vertex of my v. To find the other points, I'm going to do just like what I did before and take values on both sides of the vertex. So I know this point here is at 3, 4. So if I substitute, if I put a 2 into here, 2 minus square root of 3 is negative 1. Absolute value of negative 1 is 1. 1 times 2 is 2. 2 plus 4 gives me a value of 6. I know that was a lot there, but if I go on the other side, by substituting a 4 in there, you'd see that 4 minus 3 also gives me 1. Absolute value of 1 is 1. 1 times 2 is 2. 2 plus 4 is also 6. And then by substituting a value of 1, that's going to leave me with negative 2. Absolute value of 2 is 2. 2 times 2 is 4. Plus 4 gives me a value of 8. Which is roughly up there. And we know it's symmetrical, so we'd get the following. Oops, I missed my points. Just keep that. So our objective at the beginning was to be able to graph an absolute value equation in this notation. And here we have an A value of 2, an H value of 3, and a K value